Okay, right. So chapter 5 is about shaft and bearings. So the first subtopic or subchapter is our shaft balancing, and the other one is for bearings. Macam ada delay sikit. Okay, kita tak apalah. It's okay. Alright, so balancing means an engine or machine is said to be perfectly balanced if there is no resultant force or the coupled moment exerted by the engine or the machine frame on the foundations. So actually, the simple words is the mass or force is equals to zero. So the moment, the couple, the resultant force is equals to zero. So it is said as a balanced uh, machine. If the moving parts are not in complete balance, so if it is not complete balance, initial forces are set up that produce vibrations. So something that is not in balance, unbalanced, it will produce vibration because it rotates and it is unbalanced, so it will result in our vibrations. The unbalanced phenomenon is represented by additional inertia or mass. Okay, so mass in inertia is the rotating parts at a certain distance from the center of rotation. So if you have a similar size diameter of beams, just a beams, and it is rotate on the axis, uh, it must have the balanced mass along the beam. Secondly, if you add some mass on the beam, okay, you need balance force also. Right. So the common things that I will share, that I share for the unbalanced, balance and unbalance is about our vehicle tire, tire creator. So that we need to go for balancing. Alignment is the other thing. For balancing is to make sure that our wheels, okay, our sport rims have the balanced mass. So that's why we have a metal that we put at the wheels to make sure that it is balanced. Because if it is not balanced, it will create vibration. When it create vibration, it will reduce the lifetime of your um, anything in your car. Let's say from the unbalanced wheel, it will give the vibration to your braking system. Okay, and then it will affect your suspension system, and it will continue. Such vibration occurring at high speeds produce excessive noise. So normally we have subchapter or topics. We have cause, okay, cause, vibration cause, control and vibration. Um, it is something that we need to know. Okay, so what noise? The common terms that we use is noise, vibration, and harshness. Okay, so it produces excessive noise, wear and tear of machine parts, and gives faulty performance of the machine or engine. As a result, frequent maintenance need to be carried out. So every 10,000 kilometers, we need to check the balance and unbalance. So we need to go for balancing for our car tire and rotate it. So we have very well wear and tear of our tire. Therefore, the machine or engine must be perfectly balanced. What does this mean? What does it mean? Machine or engine must be perfectly balanced. So the forces, the resultant force and moment or couple moment is equals to zero. So this is the equation that we have. The only equation that we have in this subtopics for the polygon, couple polygon, and also force resultant force is 0, equals to 0. So for the shaft balancing, we have the first one for the static for balance when it is static, dynamic when it is rotate. Static balancing is a single plane, so it is a plane x, y, z. So we look at the plane x, y. Okay, static balance is single plane balance and obtained when the center of mass is located at the center of the body. So the center of the body will be the center of mass. So it is summation of mass. This is for mass, and R is distance from the center, the point. Okay, so the summation of MR equals to 0 comes to summation of MR equals to 0 is mass of number 1, distance of number 1, plus mass number 2, distance number 2, plus mass number 3, distance number 3 equals to 0. Okay. So this is the static balance. Dynamics. So when it is rotates, we have dynamic. Dynamic balance is multi-plane balance and obtained when the body is rotating. So when it is rotate, it is dynamics. The summation of the centrifugal force must be 0. So still must be 0 since omega is constant. Omega is constant because it is on the same shaft. The rotation is the same. It is constant. The above equation can be simplified to summation of MR equals to 0 because of our omega. So M1 omega 1 R1 and 1 omega 2 R2 omega is the same. Take it outside. The condition of the equation, the condition of summation MR equals to 0 is also the condition for static balance. So static and dynamics use the same equation. When the body is dynamically balanced, it is also statically balanced. First, when dynamic is balanced, dynamic balance, it means static balance. Okay. The otherwise, if it is statically balanced, if it is statically balanced, the dynamic it cannot be said that dynamic is balanced. Okay? Sometimes a static balance but dynamic is unbalanced. So not sure. It is no confirmation that when you have your balance of static, your dynamic is balanced. No. But if dynamic is balanced, confirm that static is balanced. This is some types of our rotating parts of mechanical machine. Okay, we have propeller, we have engine crankshaft, we have fans, we have anything that rotates, disc brake. So this is the rotating parts in our vehicles that need to be balanced. Okay. Kalau tak balance, okay, if it is not balanced, it will create a vibration. Okay, and it will reduce the lifetime of your components. This is another type, drive shaft. So we need to make sure it is balanced. Disc brake, grinding wheel, okay, a wheel balancing machine. Okay, so this is what I tell you at the early session. So we need to have our tire balance for every of our tire, 4 tires on our vehicles. Okay. For the balancing method, we have edit. We need to add mass. How to make it balance? Okay. How to make our machine, our components balance? The first one is we add the mass. Okay. We add, and the second one we exclude. Okay, we exclude the mass. Okay, so this is the initial condition. This is our problem, the main problem. We have 5 propeller that is not balanced. So for the mass addition, we add number 6. Okay. For the mass exclusion, we throw number 2 and 4. So we have number 1, 3, and 5 to make it balanced. So that is 2 types of method that we need to know to balance our system, our machine. So now we go for the approach. The first one is method. Method is add or exclude. Okay. So then how to calculate? We have 2 types of approach. First is analytical approach. Analytical approach is you use your knowledge in your mass. Okay. It is actually force. So you have this type of propeller. Okay, this is the propeller, and this is the propeller, and then you need to make sure that it is balanced. So the mass and distance of each propeller is different. Okay, each fan is different. Let's say this one is 5 kg, R equals to 10 cm. This one is 10 kg, 2 cm. So different types of mass and distance from the center. Okay, so it creates a force. So when it creates force, we look at the section. First quarter, it will give force like that one. Second, that one. Third, fourth. Okay, so the difference of mass and distance will give different force. Okay, because we have mr equals to 0, right? Okay, so we need to make sure. Okay, we need to make sure, or you can use f1x equals to f1y equals to, and this you have the theta 1. Okay, so that is the analytical approach, where normally we use cos, sine, and also tangent. Tangent is normally we need to find the resultant force. Okay, and then we need to find the theta. Okay, so summation of force, the unbalanced mass, and this is for the unbalanced, and this is for the balanced mass that you want to add. Okay, easy. Balancing approach on solving on x and y components. So we have x and y components. So we have the center and we have the force. So we need to calculate the x and y. Okay, so this is static. So sine theta, so that is theta x, y, h. So sine, cosine, tangent. So use that analytical approach. So to solve the resultant force, okay, to solve the resultant force, we just use the statically method. Okay. The first one, okay, we are giving a question. Okay, we are giving a question. This mass, this distance for 1, 2, and 3 masses, and then this that one. Okay, 1, 2, 3. So number 2, we need to find the resultant force. Okay, the resultant force of all the 3 mass. Okay, so the total force is there about the 1, 2, and 3. It is not balanced. So how do you overcome the balancing to make it balanced? You need to add. You need to add to counter the unbalance. You need to add this one. So this mass and this theta is what we are going to calculate. Okay, so this is how to solve the using the analytical approach. Okay, so we have a simple unbalance of 2 masses. We have 2 masses, which is M1, M2. That is the mass. So X is 0. In X direction is M2R2. In Y direction is M1R1. Dengar tak? Dengar bising tak? Okey tak? Oh, nampak tu.
Okey saya okey.
Gangguan? Tak ada? Okey, boleh eh? Okay, so so this is the first problem. We have mass number 1, mass number 2. Don't look at the mass number 3 yet. Okay, don't look at it yet. So we have M1, M2, the first one with 90 degrees theta, right? Okay, so okay, so the first one for analytical approach, MB, RB, B is for balancing, is unbalanced force because of omega is constant. We take it out and we do it as a vector. The first one is M1R1 going up 90 degrees, M1R1, and then M2R2 0 degree, and then we need to close our polygon to make it balanced. Number 3. Okay, so that is, this one is mass mass distance that you need to add. Okay, so it's the M1 R1 and M1 R1, M2 R2, and then you have mass for balance and distance for balance. You can let's say that MBRB is 10 kgm. Okay, 10 kgm. So you want to put that the 2-meter distance. Okay, 2-meter distance. So you have 10 kgm equals to MBRB. R is 2 meter. So MB is 10 divided by 2 equals to 5 kg. Okay. So you need to close your triangle. It is the same as this is the same as if you have x direction. Sigma fx is equals to m2 r2. So you need to counter. You need to counter the direction or the unbalanced mass and distance this way. So this is M2 R2 for your balance. Okay, and then the next one, M1 R1, you need to counter M1 R1. So you have M1 R1 for balance. So this kind of analysis calculation is from the static. So for the equation, you have M2, right? And then you have M1 R1, and then you need to calculate the R. Right. So you need to calculate the R. So M2 R2, M1 R1. So this resultant force is the same as this one. Okay, so it's just close the polygon. So this is the analytical approach. And next one, you have a graphical approach. Sama juga ni dalam kita punya the simplest way is we use our AutoCAD. Okay, so from AutoCAD we put that M1 R1 that way. Is it M1? Okay, M2. M2 R2, and then M1 R1. Finally, close the loop. So we need to calculate this one. So what is the distance? How long it is will justify the MBRB. This is the MBRB. Okay. So you can use the graphical approach. This one is using CAD, but it is not conventional. But if you are in the final exam, you can use what we call it, graph paper. Okay. Betul kan? Graph paper. Graph paper yang yang garis kotak-kotak ni. Okay, 10 kali 10. So you need to draw it using scale. Sudah. Okay, nampak tak? Nampak kan? Saya takut tersalah tekan. Alright, so using CAD or using graph paper, okay? CAD and graph paper, then you can use your graphical approach. This example is not the previous question. It's not this one, okay? So this is just the example that we can use CAD software and graph paper with the scale. So you need to mention your scale, 1 cm, 10 meter, 10 kgm, kilogram meter. Okay. Then you need your protector. You need your you need to calculate your degree. Okay. All right. Okay. This is the first example, as in the introduction. So the figure above shows a disc having two unbalanced masses of M1 and M2. M1, M2. The distance of mass from axis rotation are given as R1 for M1, R2 for M2. So M1, R1, M2, R2. The values are given below. So M1, R1 is 3 kilo 1. And then M2, R2 is 2 kilo 2. What you need to do? Okay, normally, so kita tengok M1, R1, M1, R1 with 90 degree. M1, R1. So what we need to do is, the first one, we can use the analytical approach, or we can use graphical approach. Graphical approach, we can put in AutoCAD, or we can calculate ourselves also. Okay. So the first one you need to do is you need to make a table for number 1, number 2, M, R, MR, and then theta. Okay. So number 1, M1 is 3 kg R1 mm. M2 2 kg R2 mm. MR is 3, 4 theta. We try to use that 0 degree from X direction. That one is the positive one. Okay, counterclockwise. But you also can use this one, 0 degree positive, or you can use that one, positive, 0 degree. Okay, but when you use it, you need to make sure that I understand that you assume that 0 degree is from Y direction, clockwise. Okay, so you need to propose that 0 degree is from Y direction. Okay, but I suggest that you use a 0 degree, this one, 0 degree from X direction counterclockwise is positive. Okay, so you need to look at your data, your calculation of this one. Theta is number one is 90 degrees, 0 degrees. Okay, so M1 R1, M2 R2, you need to draw M1 R1 90 degrees. Okay? M1 R1 is 3 going up, 3. M2 R2 0 degree, 4. So to close the loop is this one. So kalau kita dah biasa, it is 5 lah, kan? But kalau tak ingat, blank tiba-tiba, you can use your H or M3R3 is equals to 3 square plus 4 square. So M3R3 is equals to 5. Okay, dengan calculator. So 5. So this one is M3R3. That data is M3R3. So the angle of the masses are shown if the disk rotates at constant here. The angle of masses are as shown if the disk rotates at constant angular velocity, balance the body by this one. Ni syarat dia. MBRB 1 mm additional. Okay, that one is additional. The other one is exclude, but same at 1 mm. Okay, so for the calculation that we use just right now is for the additional mass. So for additional mass distance, MBRB equals to 5 is for the additional. If you want to balance with addition of mass. Okay, so now we'll calculate MBRB is equals to 5. RB is equals to 1 and B 1 equals to 5. So MB is equals to 5 over 1 is 5 kg. That is balanced mass. It's 5 kilogram. Okay. Okay, next. Theta. So theta, it is where you look at. Okay. This answer 233 degree 233.13 degree clockwise direction. So dia sebenarnya okay. Jawapan ni you tak perlu tengok, bukan tak perlu tengok. You need to understand that where you take your 0 degree. Okay, so 0 degree is from here, or you take it clockwise direction. So that is your theta. All right, so that is the theta. And then the next question is exclude. Okay, for exclude, you want to take out the mass at 1 mm. So actually it is the other side, the opposite side of your resultant force, that way. This is for question B. So for that one, you need to calculate the theta. Okay? To exclude, to throw away the mass of the system. Okay, right. So that is the first one of our example. Any question? So from this one, for balance shaft, we have method. Method kita ada dua, add or exclude. Add is you want to add mass, exclude you want to throw away the mass. Okay. Technique. This is approach, calculation. Okay. The first one is analytical, and the second one is graphical. Okay, so analytical is use your sine, cosine, tangent, theta, resultant force. Okay, that is analytical. Graphical, you can use a CAD graph paper. Okay, ada soalan tak? Katanya okay. So itu untuk mass balance. Next additional example, 3 masses A, B, and C. So A, B, and C dalam satu disk, in one disk, A, B, C ni letakkan balance, letakkan mass. We have A, B, C. A is 120 mm, B is 100 mm, and C is 80 mm. So 120 mm, 100 mm, 80 mm. The masses are 1 kg, 1 kg, 0.7 kg, 0.5 kg. Determine the fourth mass, radius 60 mm. To statically balance the system and sketch the force polygon diagram for the balance. The first one, you can use your analytical approach. Second one, you can use your graphical approach. But before you do that, you need to construct your table. So ini M, A, B, C. Dalam padang. Okay, A, B, C. This is M, R, M, R, theta. Okay, we have 1 kg, 0.7, 0.5. R is 120, 100, MR is 120, 70, and 40. Theta is A is, so this one is 0 degree, 0, 30, and then 180 minus 50 is 100. That is the theta. So mesh number 4 is D, which is we don't know, and the given distance is 60. So this is 60 mr, and we don't know the theta yet. Okay. So construct the resultant force, the analytical approach. We have $120. Then we have 70, and finally we have 40. Okay? That is the force. Then you need to find the resultant force. Sorry. And then you need to find your theta for MD. MDRD. Okay, so this is 60 mm for the R. Okay, so this is salah C 1.5 1 0.5 0.7. Sorry. Okay. 1 0.5 0.7 100 120 80 120 50 and 80 56. Okay, so ni 0.5 0.7. Okay, so this one is 50 and this one is 56. So we have all the three meshes, and then this one 120 50 56. This is MR. Okay, for the analytical approach, we need to divide it by X and Y. Okay, so for X and Y, 120 in X direction, cos theta, 50 plus 50 cosine 30, and then minus 56 cosine 50. Okay, 50 cos 30, 56. So this one is actually will give you negative value. Okay, right? And then Y is that one. 50 sine 30 degree plus 56 sine 50 degree. Okay, so this one is 0, this one plus this one. So you have in your X direction and Y direction. So what you need to do, you need to one 127.31, 67.6, 67.90, So you need to find your resultant force. This is for the excluding, but the question is how you can balance with the additional mass. So you need to add the mass. So from the, that is the resultant force. And then this should be your answer. M D R T to balance the machine. Okay. So you have in X and Y, so it's 1 to 7, 67.9, and then this is if you want to exclude, you want to throw away the mass on your disk, on your system. But the question is asking you with the additional mass MD. So this is your this should be your answer. MDRD is equals to this one, 144.28 kgmm. Given that the radius for MD is 60 mm, so we have MD MD 60 is equals to 144.28. MD is equals to 2860. MD is equals to 2.4 kg. Then you need to find your theta. So normally you will find this one theta, and then you need to add the 180 degree. Okay, so this is the analytical approach. Analytical approach. Next, you can use a graphical approach. Okay, you can use graphical approach. Macam mana nak cari theta tadi? Okay, yang ni kah? Cari theta yang mana satu? Theta yang ni. Dia sama je macam static. This is the same as your static, but you need to come out with your sigma MR first. Sigma MR, and this is actually your force. Okay, sigma MR is equals to force, so you come out with the same, this one. Okay, so theta tu just masukkan, and then you need to steady understanding that X is from X-axis counterclockwise positive. Buat that one. Jadikan kebiasaan. But it is not a mistake if you take that from Y clockwise direction is positive. This is not no mistake. But I'm worried that you will trap yourself. Okay. Okay. So saya example awal. Nah, ni. This one. Or this one. This one. This one kot. Kan? Okay. Okay, right. So we have M1 and what? Kita tengok kat sini. M1 R1 is equals to 3 kgmm. M2 R2 is 4 kgmm. So actually, this one is M1 R1 3. This one is M2 R2. So this one is 90 degree, 0 degrees. Okay. Dalam soalan tadi tu lah. Kan? Sebab dia buat macam ni. M2 M1. M1. Okay. So ni R2, R1. Okay. Tapi kita kena buat table dan kita keluarkan MR table lah. Because of that is our force. Force is equal to M times R. So itu force. So dah dapat force, kita keluarkan 3, 4 and then we close the loop. We close the loop. Kalau close the loop is for add. To exclude the mass, you need to this way. But this is the same. 3, 4, 5. But this one, you need to exclude. You need to create a hole throughout the mass on your disk. Okay, sebenarnya this one is something like we have this, right? So at the center, we have put M2 here on the disk, and then we put M1 here on the disk. So what happened to the balance of our disk? This is some kind like our disc brake, vehicle disc brake kan. Okay, so tambah, nak jadikan balance, you kena put some weight. Okay, the first one, you can add the weight, which is the resultant nanti kat sini lah. So this is you put the weight to overcome both weight kat atas tu, M1 and M2. Or the other method is you have M1, you have M2. That is the additional weight. You can exclude. Okay, there's a hole there. So no mass. You take it out. You throw away the 5 RR, MBRB for balance. Okay, so first one kita tengok yang ni So kita add lah. Untuk add, ada 3, 4 dan we know that hypotenuse this one is 5. Kan? So 3, 4, 5. So theta, macam ni lah, macam biasa. 3, 4, theta. Okay, theta is equals to, tangent theta is equals to 3 over 4. Theta is equals to tangent negative 1, 0.75. Tekan calculator. $36.87. Okay, so kalau kita ambil theta from here, ni this one lah. 180 plus 36.87. Okay, so this one is 180 plus 36.87 is equals to 216.87. Jawapan dia ni 233.13. Alah, dah. Bila saya keluar aja dia hilang balik. Okay, so jadinya dia macam ni. Ini 5 tadi, then ni theta, kan? So we have calculated that theta is equals to 36.87 degree. Tapi jawapan tadi 233.13. Betul. Actually our theta is equals to 180 plus 36.87 if we take from here. From theta x is equal 0 degree. Okay, but the answer is taken the theta from y positive. So this one is 90 minus 36.87 equals to, this is 53.13. So this one is 180. So theta total is 180 plus 53.13 is equals to 233.13 degree. Okay, so this is the answer from this question. But again, it is not false if you take it from here as 0 degree. But normally, and please be consistent that you will take x direction as 0 degree, counterclockwise as positive. Please normally use this way. Okay, it is not a sign convention, but it will give you some standard that you take it as 0 degree. Okay, okay, right. So itulah that is the answer. 23 ni dengan ni samalah dia ambil. It is from the y direction. Okay, y positive, clockwise direction is positive. Y 0 degree, clockwise direction positive. Okay, so itu ini dah berlalu tadi, boleh semak dan tengok balik. Okay, we can use graphical approach. Okay, so graphical approach is CAD drawing or graph paper. We look at our sigma MR. Okay, so it's not sigma MR, it's M1 R1, this one with the theta. Okay, so M1 R1, M2 R2, M3 R3. Okay, first M1 R1, we'll take it from here. M1 R1 is 120. 120. You take the M1 R1, 120. Okay, so this is M1 R1, 120. Second, sambung. Continue with M2 R2. M2 R2 is 50 with 30 degree. So take out 30 degree, sambung. M2 R2. Okay, so this is 50. You can use scale also. Okay, and then 56 with 50 degree. From here, take 50 degree, symbol 56, the distance. Okay, sampai situ je lah. That is the given from the question. That is the question. So what you need to do is you need to close the loop. So you need to close the loop and then you take, okay, close the loop. This is for the balance MDRD. Okay, so MDRD. So this is what you need to do. MDRD is equals to 144.28. And then RD is given as 60. So MD 60 equals to 144.28. MD is equals to 144.28 divided by 60. MD is equals to 2.4 kg. Okay, 2.4. All right, so that is graphical approach. Okay, so graphical approach. Boleh guna graphical approach, but the first thing, the first thing that you need to do is your table. You need to construct your table to get your MR value. Jangan salah macam saya tadi ni. Ni, ini construct masuk salah, then habis jawapan. So please be careful, double check your answer. Okay, any question for static balance sebelum kita masuk ke dynamic? Any question? Saya rasa okay, just straightforward. Alright, so kita masuk dynamic. Okay, dynamic is about multi-planar. Okay, multi-planar. We have different plane. Okay, so the different plane in one shaft. Okay, it is not like the examples of our this before this. Okay, so the break this before this is just one this on the same plane. The this is the same plane, but for the dynamic we have multi-plane. Okay, so for the multi-plane, so for multi-plane dia banyak plane lah. So the plane 1, plane 2, plane 3. So kalau solid work kita ada plane. Kan? So kita boleh add plane. So every surface is plane. Okay, so for now, for dynamics, we have a multi-plane to conduct our analysis. Okay, so balance of multiplanar rotating body is referred to rotating body that has mass on different planes. So we still use the static balance equation of this one. As I said in the early session, if your dynamic is balanced, that means your static is balanced, but not the otherwise. If your static balance is balanced, it doesn't mean that your dynamic is balanced. Okay, so plane, multi-plane. So the first plane, let's look at the plane M1 R1 is on the plane 1. M2 R2 on the plane 2. Different plane. Jauh sikit at the back. Okay. M3 R3 is at the different plane. Lagi belakang. Okay. And then we have B1, B2 balance, B1 for balance. Okay, so that is from the 3D design, 3D figure. But the question is normally giving you this one only. Okay. Giving you this one. So you have here is M2. This one is M1. So you bring it to the plane B. Okay, plane B2. So you bring it all to plane B2. Then this one is M3, and finally we have B1. Okay, right. So itu dalam dynamic, we have different plane. So dalam dynamic, in dynamics balancing, sebenarnya tak susah, kita tambah lagi satu. We add one more what we call it value. Okay, parameter. So we add distance of L. So this is the additional parameter that we add in dynamic. So dynamic balance of the shaft balancing. Okay. So we look at the some examples. Mass is not in the same plane. Consider two masses statically balanced as shown, but acting at different places along the axis. So kita ada given in the figure is a shaft, center gravity at the center, and then we have MARA at the top, and then MCRC at the bottom. So from the side, okay, from the side we have here MARA, and this one is MCRC. Okay, so that is the that will the figure for your question in the exam. So from the front side and from the side, front view and side view. Okay, so for static balance, it is balanced, but for dynamic balance, we don't know yet. Okay, so we need to calculate the dynamics. It is clear that even with static balance, centrifugal force will produce a turning moment about the center. So turning moment of gravity for the system. In this simple case, the problem is solved by adding equal and opposite forces. So senang je. So tambah MC tambah MA. Okay. Opposite direction. Okay. Consider the turning moment due to a single mass. It is actually a couple moment, a moment. Okay. So if MCRC is rotate, okay, from X direction, okay, it is force times the L. Before this, we use L1, L2, L3. So it will develop the moment. The turning moment about the reference plane TM is equal to F times X. So F is M omega square R time distance X. Okay, so F X. For dynamic and static balance, we must work out the resultant turning moment and add masses at appropriate points to cancel it out. So kita nak balance. The appropriate points will be on two planes not coplanar with any of the original masses. This involves drawing two vector diagrams, and since omega is common, all vectors, omega is constant, assume as 1, and we take it out. Okay, take it out. So for now, we have, again, this is sigma is equals to mr, and summation mr equals to 0, and times x, summation of mr times x equals to, kenapa tulisan jadi? Ini kurang hilang, sangkut. Okay, so equation. Balancing approach, dynamic for dynamics balance, as figure, shown in a figure, okay, simply select one plane, reference, one plane as a reference. As a tip, select the one that less information like mass, radius, or angle. For symmetrical system, symmetric axis is selected as a reference plane. This reference is for static analysis. So for this balancing, determine the positive and negative direction. So one reference, positive and negative direction. This one is, we call it X, or from the previous figure is L. Okay, your L. Multiply the term by m omega square r. Okay, m omega square r times L is actually L times X. Okay, but omega is constant. We take it out and we have this one. Okay. Okay, so now select a reference. So for reference, let's say that B, we take B as a reference. So this is 0 and A is negative direction, C is positive direction. We take it as reference. So we need a reference for the plane. Okay? We need a reference for the plane to construct our table. Untuk balancing, shaft balancing, buat table lebih mudah. So now you have, let's say this example ABC. Okay, ABC, you have MR. This one is MR. And now additional is L. And then you have MRL. Okay, and of course your theta. Theta. Okay, that one is the first one. And then you have another thing is X and also Y. Kalau ada bearing, ada reference. Okay. So L ni nanti yang akan jadi negatif ni, yang kat dalam ni. So bila L negatif, sini akan ada negatif. Okay. So just use that as the reference. Sama juga analytical approach to determine the unbalanced resultant force and resultant moment that exists. We have force polygon. This is for MR. This is for moment polygon is MRL. Okay. So we have the first one, static balance, X direction, Y direction. Now we have L term for our dynamic balance. Okay. So this is a moment polygon. Number 2 equals to 0 in x direction and also y direction. Okay, all right. So this is analytical approach. It is the same sine, cosine, tangent, resultant, theta. Graphical. So graphical approach. The first one we need to do is for the MRL, and then baru kita buat MR. So MRL is a couple of moment polygon. Ni force polygon. So first one dulu kita buat MRL, baru kita boleh kena buat dynamic dulu, dan baru kita boleh settlekan static. Okay, so ini je tambahan. So dalam contoh graphical approach yang ada ni 0 degree negative value, and then dia tambah M2R2 tambah ni theta dia lah, M3 R3L, M3 M4 R4L. So dia sampai sini je. Then to close the loop, you need to close here to here. Okay, so this is the balance couple of MRL balance. Okay, itu je tambahan. That is the new additional method for the dynamics. Okay, graphical approach. Find vector. Okay, the first one is find the MRL, and the second one is find the MR. So this is MRL, and then dah jumpa MRL, for balance, mesti ada satu jawapan ataupun one information. It is either L or R or M yang diberikan, is given from the question. Okay, so from that we can settle MR or ML or RL. Okay, so ini kemudian kita cari R. Okay, so dapat R, masukkan dalam table, and then you need to draw your MR force polygon. Okay, so boleh guna analytical approach or you can use the graphical approach, but you need to close the loop. So from the MR, from the table, you draw the graphical approach, and then from here, this is here to close the loop, and this is the MR. MR balance. Okay, so dapat dapat selesaikan. You can solve the MR static. Okay, example. Macam panjang ni. Okay, for example, the shaft above carries two masses M1 X1, M2 M1, M2 R1 R2. Two bearings X and Y. So ni bearings, ni bearing. Show the angle of masses, and diagram shows the location of mass and bearing plane. The mass value, radius of rotation R, and plane location. So diberikan ada ni. L3. By taking plane X as the reference, balance the body when the shaft rotates at P1 B2. Okay, so ini B1, ini B2. Okay, so kena construct table. Okay, first construct table. Kita ada M1, M2, B1, B2. So construct the table and then masukkan nilai MR and then given B1 3 and 1.67, B1 and B2 distance. Yang kosong tu yang kita tak tahu. We don't know. Okay, we don't know. Okay, this is the answer lah. Okay, so first one we need to use our MRL. Construct the table. Sekejap, Okay, so construct table MR, additional L for dynamic, so you have MRL and put your theta. Okay, theta 90, 0. So masukkan. Look at your table and then what do you have from table? Okay, now you need to take a reference. Okay, for MRL. Okay, so the first one is you need to taking a reference. So reference is 0. So B2 is 0. So we don't have MRL because L is 0. Okay. So now what we have is our M1, M2, and B1. So we need to solve this one. This is number 1. We need to solve. So from the analytical approach, or we can use graphical approach. So for the analytical approach, we have 3, this one, okay, 90 degrees, 3. Then we have 8, 0 degree, 8, 0 degree. Now we need to close the loop. Close the loop. So this one is 3 square plus 8 square. Okay, 3 square plus 8 square. This is the M B R B L B equals to 8.54. 8.54. So that is the MRL. So now you have 8.54 kgmm. Then go back. Go back to find your given M and R. So 8.54 MRL equals to 8.54. You have M is equals to okay. M 8.54. Berapa tadi B1 tadi? 3. Salah. 3 kali 1.9. Okey. 3 1.9 kali L sama dengan 8.54. So ni M R L. Okay. So 8.54. So L is equals to 8.54 divided by 3 equals to 1.498. 1.5 meter. Okay. So MRL dapat 1.5 meter. So selesai. L 1.5 meter. 3 kali, patutnya ni boleh masukkan. Ni 5.7. Okay. So selesai ni number 1. Then baru buat this one. Number 2. Okay. So dapat tadi 8.54 dengan 1.5 meter. This is for MRL, and then you boleh calculate lah tadi. Calculate 3, 8, 8.54 kan? Okay, so theta daripada sini sampai sini. Okay, so 20.56 is this one. Campur dengan 180 dapat dia punya theta. Dapat 200.56 degree. Okay, so okay, so that is the MRL. So kita dah solve MRL. So dapat L. Okay, now we are solving MR. MR tadi kita tahu M diberi. So kita kena cari inilah. So again from analytical approach, and also you can use from graphical approach. So kalau graphical approach, sini ya. Graphical approach 3 4 lepas tu 5.7 200. Lepas tu next kena close. So itu yang kena cari. Ataupun you can use your ni 3 4 5.7, and then cari resultant force, and then cari theta. Okay, so kita guna analytical approach, which is sine and cosine. So we have this one lah. Saya pelik kenapa dia bergegar-gegar. Kalau screen. Okay. So macam tadilah yang saya buat. So kita ada 3, kita ada 4, 3, 4, and 5.7. So 20.56. 6 degree. So ini je lah yang kita kena pecahkan kepada X and Y direction, so that we have ni tak ada. Okay. So this is a value for X, this is value for Y. So we draw the resultant force or triangle. Okay, a triangle negative 133. Dalam kes tu tadi, the resultant force is negative 1.33 and then Y positive 1.0. Okay, so ini resultant force dia. Kan? So untuk balance ni. Okay. So both, you can use both analytical approach and graphical approach untuk dapatkan jawapan. But for me, untuk graphical approach, this one, okay, this one, graphical approach pakai CAD or graph paper, okay lah, kan? But to show the calculation, you need to use your analytical approach, X and Y. Okay, so dua-dua boleh guna dan kena fahamkan lah actually. You need to understand what method you use. Okay, so this one is the same question using graphical approach. So you have 8, macam saya lukis tadi, I draw this one 3, 8 and 8.54. Tapi ini dia ada way around, dia lukis 8 dululah. So 8 soalan ni lukis 8, lepas tu 3, lepas tu close. 8.54. Okay, itulah dia. Dan untuk MRL, so this is for moment vector MRL and this is force vector for MR. Okay, buat table. Buat table MR, MRL, and then you need to kosongkan, isikan table yang kosong. Question. Kita ada 3, 4, 5, ada 3 lagi example. Okay, 3 lagi example. Dan kita ada petang ni ada kelas ke? Lepas pukul 4 ni. Kita nak buat quiz. We have quiz also after the class. Ada kelas tak petang ni? Pukul 4?
Tak ada.
Tak ada.
Tak ada.
Okay. Sekejap. Ini nak tengok. $20. Okay. Boleh saya sambung ya. So kita dapat habiskan yang balance . Tunggu saya nak buat video, memang tak buat-buat. A rotating shaft at constant angular velocity carries 4 masses A, B, C and D. So ada 4 mass rigidly attached to it as shown in figure. So front view dan juga side view. So ini front lah, ini side. Rigidly attached to it as shown in figure above and the center of mass. Okay, so ini kena hati-hati. Ini R1, R2, R3, R4. The mass A, C, and D. Okay, so ni A, C, and D. So B tak ada So B tu kosong. 75, 5, 4. Bukan kosong. I mean no information about B. So this is A. Kanan. Tulis A pun jadi 8. A, C, D. The axial distance between A and B is 400 too. And B and C is 500. 500 too. The eccentricities of A and C are 90 degrees. If the system is fully balanced, so ini balance. So everything is equal to 0. Nak cari jawapan B dan X ni. Okay, if you got question like this, what is the first step you need to do? The first step. First step nak buat apa?
Lukis table.
Yep. Correct. You need to draw your table. Okay. Answer dah. Okay. Macam mana nak buat? Sebab kalau saya keluar nanti dia hilang. Prime. Saya tengok dia sampai tak. 7, 5, 5 and 4. Okay. Draw table. So draw table. Kita ada tengok dia tak nak. Saya punya pencil tip ke? So kita ada A, B, C, D. Okay. A, B, C, D. Anggap je lah dia straight. M, R, MR, L, MRL, theta. 7.5, 5, 4, 30 mm, 36, 39, 33. Okay. So calculate MR 255. We put it as MB, 36 MB, 195, 132. Okay, so from A, B, C, D. Ambil, normally kita akan ambil B ataupun the second plane as reference. Okay, sebab nanti akan senang untuk kita eliminate sebab dia kosong. So this one is negative, this one is positive. Okay, so L is equals to 0.4, 0.5, X. Plane L kena ambil daripada reference. Ingat, L kena ambil daripada reference. Okay. So reference B kosong, L negative 0.4, 0.5, 0.5 plus X. Okay, so MRL is equals to 55 times negative 0.4, negative 90, 0, 97.5 plus 132X. Okay, and then given CA, okay. CA, C kosong A 90 degree. Okay, lain tak ada, theta. Okay, what table? Draw your table, include all the MR, MRL, and theta. Now, this is the first one. Okay, so this is the first one. You need to draw, and then barulah you boleh buat MR. So MRL. Okay, so for moment MRL, negative 90 degrees. So positive is going up, positive. So negative value (90) going down, 90. And then 0 tak ada, 97.5 down. Ciao. (90) 97.5. Okay, then close the loop. This is what? This is 90 square plus 97.5 square. Can? So this is equals to 90 square plus 97.5 square. 132.7. 132.7 is this one. 66 plus 132x equals to 132.7. So x is equals to 0.5. Now we have our x is 0.51. So this one is actually 1.01. Okay, that is number one. Number two, we need to solve this one. Okay, belum. Actually, you need to find the theta. Okay, so bila dapat theta, and then you know your theta b. Theta is from here. Okay, you have your theta b. Theta b is equals to, it's not theta b, theta d. Sorry. Okay. So theta D. So theta D is equals to 127. Okay, so dapat theta D number 1, number 2, number 3. So kita selesaikan number 3 pun sama juga MRL. Sorry, MR. So MR is equals to 255, 90 degrees going up, 255, and then C 195, 195, and then 132, 127. Okay, so kurang lah. 132. Now you need to close the loop. This one. Sorry. Okay. So that R is 36 MB. Okay. So that R. So kalau if you are using the tengoklah di detail. Dia punya tip ni lah. Okay. So ni pun sama. If you are using this one, so you have this one is 255. This one is 195. This one is 132. Now you need to find the resultant force, and then you need to opposite the force. So kita ada ni lah atas total. So normally dia akan ke sana lah. So this is the resultant force, and then you need to balance. This is this one. Okay, so this is graphical, this is analytical. Okay, so ini dah hilang ni. Itulah jawapan dia. Tadi kita dapat the axial distance x 0.51 meter, and then the angle of mass CND axial distance theta D equals to 127 degree, and then mass B is MB is equals to 10 kilo. And theta is 100. Okay, kita boleh check balik video dan kita kalau salah boleh. Ni mungkin tak betul, bukan tak betul apa. Dia punya x 0 ni. Ni yang ni. Kemungkinan bukan daripada x direction. Okay, so check. Okay. Ni answer dia dah. So ni pun find the mass and the angle at which it should be positioned in planes A and D. So B, C, 60 degree, 75, 50 M. So again, M B, C, R, 5 to 75, 50, MR, MRL, sorry, L, MRL, theta. Okay, buat dan addition kita ada A and D. Okay, so ni boleh try buat soalan, kalau tak dapat nanti bagi tahu pun sama. Okay, MRL, theta, and then MR. Okay, ini saya dah upload dekat dalam Ulearn. Okay. Next, saya bagi last lah, ada example 5.4 and 5.5. Tapi saya buat 5.4 je lah. Okay, boleh tengok dah faham kan. A shaft 1.3 meter, total shaft ABC 8, 10, 6, 60, 50, 40, and R direction of eccentricities of B and C relative to A 60 to 70. Nampak? So, ni 60, ni 270. Maknanya dia ambil sini as 0 degrees. Okay? Alright, so sama juga reference. Okay, so from reference, buat table, selesaikan MRL, selesaikan MR. Okay. Ni answer terus juga. Sekejap. Itulah. Okay. So kita ada A, B, X. So kita kena form a table. Saya tunjukkan lah. Boleh. Note ni nanti saya save dan saya akan upload dekat dalam Ulearn jugalah. Okay. So A, B, C, X, Y. Okay. So A, B, C. Okay. Sebabnya juga A, B, C. So ini X, ini Y. Okay. Tapi yang ni tak ada. I mean bila I off slide, I conteng yang ini, this one, this page lah, tak ada. Sebab bila keluar, bila up je dia hilang. So kena guna strategi lain nanti. Kena tambah slide. MR, L, MRL. Okay. So buat ni ambil reference sini. Negatif, positif, 0.2 meter, 0.5, 0.3, 0.3. Okay, so tadi diberikan 8, 10, 6, 60, 50, 40. So now you have your MR is equals to 480, 500, and 240. And L negative 0.2, 0.5, 0.5, 6, 1.1. Negative, so ni calculate to 50, 260, 0. Tengok dia ambil 0, yang A itu 0. So dia ambil 0 kat situ. Okay, 0, 60, 270. So dia kena macam ni. Okay, so that one dah buat graph. Apa lagi yang diberikan? MR, MRL, RX. So ni RX, RY. Kosong point 5, kosong 8. Okay, dah. So MRL is 0.8 RY. Okay, so B60, okay, betul. So ini theta X, theta Y. Right, so itu that is our table. Now from reference, and then we need to solve this one. Okay, so untuk solve that one, boleh pakai XY negative 96. Sekejap. Tengok. Sebab dah hilang. Tak apa. Ni dia ambil ni yang kadang-kadang confuse. Ini dalam contoh dia buat kosong sebab nanti kalau saya buat jawapan kosong saya banyak nak kena calculate. Okay, so boleh buat tadi negative 96 and then tengok negatif ke bawah lah. So kita ada XY negative 96 B250 ni 60 kan, jangan salah 60, so ni 250 and then kita ada C 264, so ni MRL softkan. Or you can use this one. Sorry. Negative 96. Negative 96 and then B 250, 264 and this is the closed loop. So this one is actually sama dalam MRL tadi, MRL A X B Y C. Kan? So dalam MRL kat sini tadi kosong 0.8 RY. Okay? So R ni sama dengan ni. Dia punya scale. So kalau graphical, kalau you use AutoCAD, kita dapat 58 lah plus minus ataupun graph paper. Kalau you guna analytical method, let's say 88, samalah ni. Okay, so sama. 0.8 RY is equals to 58. So you can get your RY is equals to 72.5 kg. Ini load dynamic force dekat Y. Okay. So untuk habiskan dynamic force Fy equals to Ry omega square kg mm. Ini kg mm. So minus times 10 to the power of negative 3. Kita dapat 0.0725 kali dengan omega square. Kita bagi RPM tadi kan. Keluar equals to 0.0725 times 2 pi n 90 RPM tadi ya. Divide by 60 seconds. 6.44. Okay. Itu MRL. Belum selesai lagi. Kita ada MR. Okay. So MR pun sama, you can use analytical approach and you can use graphical approach. Okay. So that one, I leave it to you for MR to find the answers, but I think is it given 6.17 and okay, this is the graphical approach to find the MR. Okay, so this is the graphical approach of MR table. Okay, so guna scale and then dapat resultant force. Okay, so this is for MR. So example 5.5, I leave it to you untuk buat latihan for you to exercise. Dan kita ada ni sebenarnya. So tengoklah, kalau tak faham boleh tanya untuk example 5.5. Okay, that's it for now. Okay, so sampai sini saja untuk shaft and balancing. Kalau ada apa-apa soalan boleh tanya, dan memang satu soalan untuk shaft and balancing ni akan masuk final lah. Right?